Joseph Bonneau. He's a professor at NYU at the Courant Institute and tech fellow, or a technical fellow at the Electronic Frontier Foundation.
Formally.
Oh, formally?
Yeah.
Oh, that's a loss to the EFF.
Yeah. Well,
I'm sure you're doing
goes on. What? Yeah. Great. Okay. So I'm going to talk about lotteries, publicly verifiable lotteries, which is another exciting thing happening. Hopefully getting to be a hotter topic. Never as hot as voting, but.
Underlying connotation that blockchain is a lottery.
Yes, I will try to convince you that that's true. Already a good question. I haven't even gotten past the first slide. Okay. I guess I'll give you the cryptographic abstraction of what a perfect lottery would look like first, and then we'll sort of, slowly look at how we can build something like that. So cryptographers came up with this idea of a randomness beacon. I believe the term dates back at least to the 80s. You can think of it kind of as an ideal functionality or an oracle that just spits out randomness all the time at regular intervals. Nobody can predict it. Nobody can manipulate it. Everybody sees the same randomness. It should be reliable. It should always be accessible. And hopefully it produces lots of randomness, as much as you could ever need. So obviously, if this object existed, that would be the end of the talk. You would drive your lottery based on this randomness beacon, and that would be it. Oh, and I'll add one more property, which I won't talk too much about, but can't stress enough. Whether or not the public believed that this beacon was actually legitimate would of course be important. So there are a lot of different things that you could build or make better. I mean, I guess we know how to do these things, but they would be better if we had an ideal randomness beacon. Lotteries was in the title. I'll show you why they're also useful for zero-knowledge proofs and consensus protocols in general, although, as I said, I'm going to show there's a little bit of a nexus. Consensus protocols, at least efficient consensus protocols, end up having a lottery running under the hood. Why are lotteries actually important? Answer number one is that they're fun. Humans have liked gambling for a really long time. That's very unlikely to change. So as long as people enjoy games that are random, whether they're for money or just video games that are fun, where you want to face, say, a changing map or whatever, there's, I think that should be enough, reason in and of itself. But there's also social reasons that we want to have lotteries, because there's some resources that are not perfectly divisible. For example, on the left here, you can see some people signing up, registering for the US diversity visa lottery, which is a process the US runs every year. 50,000 visas are given out by lottery. Usually there are somewhere between 3 and 5 million applications, of which 50,000 are randomly chosen, which are then eligible to receive a green card for the US. Lots of other countries also run immigration lotteries of one form or another. School lotteries are really big. There are a lot of jurisdictions in the US and lots of other places where spots in schools are allocated by lottery. And the common link here is that you can't give somebody, well, I guess you could sort of give somebody a visa to live in a country 6 months out of the year, but mostly people would like to move completely. So if 3 million people sign up for 50,000 slots, you can't just give everybody a small fraction of a visa. So we typically turn to lotteries in those cases. Of course, there's other ways you could solve this problem. You could try to determine it based on some sort of value or contest, but in practice, lotteries are quite useful. And then in the middle there is sports, of course. When you're running a big sports tournament, you have to decide who plays who. Usually that involves a lottery. These are actually some of the most high-profile lotteries that are out there. There are also a lot of applications of lotteries that people don't think of as lotteries because we don't use the word lottery. I would call them negative lotteries, but they include deciding who gets picked for extra security screening, deciding whose taxes get audited, deciding who is subject to the military draft in some cases. That hasn't been the case in the US since the 70s, but we did do conscription via lottery. It's happened in other countries as well. So these are, mathematically, it's exactly the same. You have to randomly pick some people out of the population, except I guess these are lotteries that you don't want to win because they have negative consequences. But they're important. And in fact, the nexus to the earlier talks, we talked about random or risk-limiting audits. For those to be secure for election, you want to randomly select which votes you actually audit after the fact. Right, if you have an adaptive adversary that knows which votes are going to be automated, if the adversary knows which votes are going to be audited, they just wouldn't cheat with those votes. So I guess that was kind of an interesting example this morning of how a lot of security protocols just assume you can randomly audit something, and that that you'll have some security if that's the case. Okay. So this slide might be fairly obvious if you have a computer science background, but if not, I guess I'm mostly just trying to convince you that only one step of this is actually hard from a computer science standpoint if you want to run a verifiable lottery. But generally, you would publish some algorithm, which is the rules of the lottery. For example, in the immigration example, it's not as simple as just picking 50,000 winners out of 3 million applicants. There are caps on how many people from each country can win, and a number of other small rules. So you'd code all that up. You'd have a period where people can audit and see that hopefully the algorithm that you wrote down makes sense. Then when it's time to actually do the lottery, all you need is a random seed. In fact, you only need a very short random seed. Most cryptographers would be happy if they had 128 random bits, and then you can use a pseudo-random number generator to do whatever you want with an algorithm at that point. So you have a short random seed. Some authority runs the algorithm, and then there's some process for independent verification. And I guess going back to Ellie's talk earlier this week or others, there's a lot of different ways you could imagine verifying that this algorithm was run correctly. A proof could be provided, it could be re-executed, etc. Okay, so like I said, this is all fairly mechanical. The only really challenging part is getting that random seed. And that's basically where I'll focus for the rest of the talk. But just I guess for the non-computer scientists in the room, actually not sure, is the room mostly computer scientists at this point?
Hands up if you're not a computer scientist.
Oh, myself.
Okay, so.
But being in computer science doesn't mean that I know what is algorithm commitment, because for this you have to be computer science / cryptographer.
Sure. Okay, yeah. Well, I guess this isn't really a cryptographic commitment. This is really just publishing it on your website and agreeing that that's what's going to be run. And of course, I'm leaving a fair number of details out here, but just the high-level structure. Okay. So I said I would talk a little bit about some other applications. The connection between randomness and zero-knowledge proofs. The basic structure of most or all zero-knowledge proofs. There's a verifier who, at least in an interactive proof, there's a verifier who makes some queries of the proofer. They get some responses. These queries have to be randomized, at least for the thing to be zero-knowledge. So, conventionally, these are usually portrayed first as an interactive proof, and then, we know the Fiat-Shamir transform can always make a non-interactive proof. If you have a randomness beacon, you can do a non-interactive proof. I guess you also need I guess this should be a time-stamping service, but you can get rid of the challenger completely. You can just have the prover publish some proof commitment, wait for the next time that the beacon publishes, and then automatically extract from the randomness that the beacon is publishing a set of queries, and then they can answer those queries. So in the case of a blockchain, you could think about basically simulating the fact that there should be a challenger, but you're using some beacon, which I'll show you later, could be generated from the blockchain. So the whole thing can just be published in that way. And you could ask, what's the point of doing this? And the reason really is just that you need to answer fewer queries to get the same soundness in this case compared to doing fiat-Shamir. With fiat-Shamir, the prover is allowed to grind and try to find a set of queries that they can answer. And in this case, they can't. It's sort of a one-shot opportunity for the prover. So I'm not aware of anybody actually doing this on blockchains, even though it's kind of an interesting idea. Actually, if anybody knows if this has been, it's been proposed off and on several times over the years, but I'm not sure if anyone has actually started doing this. I guess we should have a lot of zero-knowledge proofs experts here, so if no one in the room has heard of such a thing, then...
Treating it from a randomness beacon as opposed
like
to...
specifically on a blockchain.
We contemplated doing it, but like, no, we're not doing it right now. Like using the randomness from the block.
Blockchain, yeah, to produce your challenges and then sort of answering them as a...
Advantages because you can use a lower security.
Yeah, exactly, yeah. So yeah, so it's a neat idea. Maybe someday its day will come. Hasn't come yet, but certainly a possibility.
It would be a lot more attractive once not only there is beacons that are really reliable, but also you can put out challenges often enough, and then you can also block them without knowing when your latency is going to...
Right. Yeah, so in the future when you really every block can be viewed as a beacon output, then this might start to look better. Okay. And then other application of randomness beacon, consensus protocols. So why is randomness important for communication-efficient consensus protocols? If you want to let everybody talk, then fine. You don't need randomness necessarily, but that requires everybody to communicate. What most kind of blockchain-era consensus protocols do is some form of a random selection of a committee of participants. And this has to be random. And then this smaller committee actually runs effectively a consensus protocol. And of course, the committee has to be big enough that if you have an honest majority in the full set of people, you can still assume an honest majority on the committee and so forth. But this basic structure of selecting a small group from your full set of possible validators and having them be a committee shows up in lots and lots of protocols in the blockchain space. So it's kind of a powerful idea.
By the way, the miners, the blocks in a miner in a Bitcoin is not a random beacon.
Why isn't it?
They flip a coin until somebody...
I'll get there. I'll show you some problems with it. But yeah, it's used as one, but there's some issues. Okay, and the historical analog of this, really cool, going back to the Greeks who had the idea of randomly selecting a parliament effectively. I've never gotten a good explanation of exactly how this device works, but involves citizens putting kind of a coin in or a token, and then a random set were chosen to serve as parliament. So this is a cool historical idea called sortition. There are some political scientists who've even proposed it in the modern era who've said, if we just had 100 random people be the US Senate rather than people who've gone through the process to become senators, we would actually possibly get a better result.
Way better.
Yeah. So, some people are convinced of that, but who knows? And so there's kind of this trilemma, can't get all three between your consensus protocol being efficient, communication-wise, doing kind of a random subsampling of participants, and being adaptively secure. So like I said, if we don't really care about communication efficiency, we've known how to do Byzantine fault-tolerant consensus for a long time. The problem is that, classically everybody has to talk. And if you're not worried about adaptive security, you can just sort of run a blockchain and rotate a different person as the leader every time. The problem is that, in that case, the attacker sort of knows who's going to be a leader in future rounds and can corrupt those people. So most protocols, at least that I know of, raise a hand if there's a good counterexample that are run in the blockchain space, whether it's Nakamoto consensus, Bitcoin, proof of stake protocols. They aim to be adaptively secure and communication efficient, which requires having some random selection of people. That's, I think, necessary but not sufficient. You have to do a lot of other things to gain adaptive security. It's like a hard problem, but you need the selection of active players usually to be random. Yeah.
I didn't quite catch that. I thought I thought that there effectively is some random selection. I mean, you're picking the block leader. I didn't quite.
Oh yeah. So that's why it's over here. It's like far away from no random selection.
Oh, I see.
No random selection, it means deterministic.
Yeah.
No random.
Yeah.
I'm confused. Why is that a feature?
What? No random selection? Well, it's not necessarily a feature. I mean, well, because you have to have a randomness beacon, right? I mean, like all these protocols have to build, like the proof of, it's like something you have to bake into the.
Someone subvert to the
oh yeah.
And there would be a particular point to kind of say violate adaptive security.
Yeah, I mean, like, look, to take a very specific example, like if you look at Algorand, like if the VRF broke, right, then if the security was not, like if you could undermine, if you could predict other people's VRF outputs, then the security proof would collapse, right? What? Just the adaptive part, yeah. Well, yeah, it wouldn't be secure against a adaptive attacker anymore. Yeah. Okay, so, sure.
Is there a formal name for this consensus trilemma?
Not that I know of. No, it's well, it's a folk theorem, so I don't even know if there's a formal proof for it or a formal name, but I think it's like an idea that's out there.
So will it be?
Oh yeah, it's different. Yeah.
There are lower bounds, not for like random selection in particular, but for not using randomness, right?
Yeah.
So PFT does require sort of so many rounds and things like that if you're not using randomness, right? So
yeah.
Those are like formal theorems, not folk theorems.
Right. Yeah. Okay. And then this was, I guess, a question I was anticipating. Is where's the randomness in Bitcoin? Well, basically the randomness is we don't know who's going to solve the puzzle next. So, one way you can view the computational puzzle in Bitcoin is it's just a very expensive way to get a randomized selection from the pool of people the pool of miners essentially, and it's weighted or it's randomized over the amount of computation that everybody's performed. So that's not the only thing that proof of work is doing. It's probably doing more than just randomness, but that's one thing that it provides is it gives you a random selection over all the miners. Okay, so how can we build a randomness beacon? The first thing people usually want is some sort of cosmic or at least
I thought not the randomness in who will be the miner that will succeed, but there is a lot of when Ajax equal Y, there is a lot of X's that will go to the Y, and
true.
The way that they are looking, they choose really randomly in some way one X out of all the one possible.
Well, so you can think about like why do they choose randomly? If they didn't choose randomly, then the largest miner would win every time, and it wouldn't be good, right? So everybody has an incentive to actually.
So the value is random, not which miner will succeed is random.
Well, they're both random, right?
One is a random variable, the other is a random function from that random variable.
Yeah.
So some other. So it's also random variable.
Okay. Like I said, the first thing people usually want to do to build a randomness beacon that doesn't work, but it's worth moving past, is to extract the randomness from some sort of natural phenomenon that we believe humans can't control. So people say cosmic background radiation, solar flare activity, sometimes weather. These are big processes that aren't predictable by humans or controllable by humans yet. Like a few small exceptions around weather. They in theory, like, seem really appealing as a way to generate random values, but they're not unanimous. So, you know, if we want to have a randomness beacon, which is just the temperature in Berkeley for the day, really depends on exactly which location in Berkeley you're measuring. You might, you know, cross over from 72 to 73 degrees on one side of the street to the other, and of course the thermometer that you're using and everything else. So it's sort of interesting. You sort of need a consensus protocol around what your measurement of the natural world is. So it turns out, I think, to not be very helpful.
It's not completely a Poisson, pure Poisson process?
Well,
it's memoryless.
yeah, but it's like we have to measure it, right? And I might measure it. My measuring equipment might get a different reading than yours, right? The issue is just that we may not agree on the value, right? So if you have like a trusted party who can measure it, then it's fine. So speaking of trusted parties, there have been some services that have explicitly tried to be beacons that are just run by a trusted party. So NIST in the US, this one has actually been stood down, I believe, so it's not available anymore, partly because nobody was using it. But while it was running, they have an open project actually to do sort of a beacon 2.0. But while it was running, they generated what they claimed were 512 bits of true randomness off of this. They had some physics set up in the basement in Maryland. That was great, but you know, you had to trust NIST that they were actually running this and that they weren't just making up the values to be whatever they want. What? It was every 60 seconds. So you could get about 500 bits every 60 seconds. So it's pretty good, but you know, the trust model was trust NIST. And then, you know, random.org, a lot of people actually point to this, which is kind of scary because it's really just a private company that runs this. And they don't even really provide a lot of details about where they get their random numbers. So obviously not very satisfactory solutions. What?
Get that .org. Just, you know.
Don't Cloudflare have like a public randomness beacon from their?
Yeah, from their lava lamps. But again, yeah, it's an.
What if I take these two sources? I don't think that random.org will. I don't suspect that random.org
Yeah.
will be in the same port as NIST, and just take the two randomness and.
We'll come back to that. Yeah, we'll come back to that, but it's possible. Okay, and then you know the other thing people say a lot is like, why not just have the trusted party demonstrate how they're generating their randomness, have them roll some dice, which is a great idea because it's really old and it's still done all the time. So this is kind of the state of the art for a lot of state lotteries, FIFA, the NBA. They still do lotteries, you know, all the time that involve physical things moving around and being drawn out of hats or other places. Of course, you know, like a good magician should be able to fake this, right? Everybody's seen a magic show at some point in their life, and magicians do like far more impressive sleight of hand than, you know, picking a ball that they, you know, a specific ball out of the bowl. And in fact, there are lots and lots of cases where this has actually happened, one of which turned into a movie that happened in the 80s. There was like another one in Serbia 2 years ago that involved a bunch of people going to jail, but these were, you know, state lotteries that were on television and were actually rigged. And in this case, the attack was really simple. They were drawing, well, they had a machine, like a rotating kind of plastic sphere, and the ping pong balls would come out the bottom of it. And they just put lead weights in the ping pong balls that they wanted to come out first. And apparently that worked effectively enough for them to make some money, but then I guess they went to jail. One more story, because this is also a pretty interesting one. Trying to do a physical randomness display, it can also fail kind of accidentally and generate bad randomness. And the famous example, the first time the US did a draft lottery, this actually happened. The reason it happened, if you look at these two pictures, you kind of notice that they put all of these, so there were 366 capsules in here, one for each day of the year, and people were given a priority order based on their birth date. So you notice, though, that the drum is in this orientation when the guy is reaching in to pull the capsules out, but it was on the horizontal orientation when they were actually rotating it. So what happened is that they loaded all of the capsules in order while it was sitting vertically, and then they turned it over on its side and they rotated it, which kind of worked, but it doesn't provide very much mixing kind of left to right. So when they flipped the thing back over, they'd mix much more in one direction than up and down. The things that started on the bottom were generally still on the bottom. And then, of course, a human is pulling them out and generally pulls from the top first. So I think it was like 5 days after they published the lottery results, a statistician who worked at NIST did a scatter plot and ran some statistical tests and said, there's a really big problem. These results aren't random. There was a bias against men who were born later in the year. The Pentagon, the US military, looked at this and said it would cause too much chaos if we basically tried to redo this, so they classified it for 30 years. And then they published the report, so we sort of know what happened now. But it's just kind of interesting that, I suppose, with modern crypto, this problem maybe matters slightly less because we know about extractor functions and things, but it's hard to gauge how much randomness you're really getting out of these big public displays. One other example, which is really interesting actually, there's a phenomenon that was very, very common in the US about 100 years ago called the numbers game. And it was basically a lottery that was run by organized crime. So state lotteries in the US didn't exist until the 1950s. They were illegal everywhere. And as a result, since people still like to gamble, the lotteries were run locally by organized crime. So there were all these different crime lords in each city. And it was actually the #1 source of revenue for organized crime. So before drug dealing and extortion and everything else, they made more money by going around and selling these tickets. And basically, you just pick 3 numbers, and you bet, this is just how much you bet on each set of numbers. And then they would come back the next day, and they would pay you if you had hit the winning 3 numbers for the day. And how did they pick which 3 numbers won? This is like organized crime, so they had a trust problem. They had to convince people that it was honest. So they did something very simple. They just took the last 3 stocks listed on the New York Stock Exchange, and they took the low order digit of each stock price, and those were the 3 numbers. And if you predicted those right, then then your policy would win. So it's actually not a bad idea, and it's still using asset prices more generally is still like a very real idea. But the problem if you do this at like a very high level, so people on the street betting $5, it's a fair bet that they can't manipulate stock prices very easily. But at the high level, there's ways to manipulate stock prices. So if you're able to make trades at the end of the day, there's a lot of different ways that you can push numbers up or down. So this is kind of like close.
But not the least significant digit. This will be.
Oh yeah, you can. Yeah, high frequency traders can do it. Like if you give them a budget and you say, I want the price of Apple to end in a 9 tomorrow, like they can do it.
Every investor that goes there changes the least significant bit.
Yeah, but the high frequency people can go last, right? So it's hard for a lay trader to do it, but the big firms, especially if only one of them wants to do it, they can do it, right? So this is like close, but doesn't quite work. Okay, so that's kind of it for story time, and now I'm going to talk about crypto. It's a good time to leave if. Okay, so I'll basically show you 3 different families of generating randomness that's cryptographically verifiable in kind of the multi-party setting. So not yet the full permissionless kind of blockchain setting. So the classic one is a commit reveal protocol where we're just dealing with 3 parties here. Every party commits to a random value. This is a cryptographic commitment that's hiding, so everybody can publish their commitment. It doesn't give you any information about what's been committed to. So you have some deadline, everybody commits to a random value. And then everybody opens their commitment, so they reveal what they committed to. And you somehow combine everybody's random values. You can hash them together, XOR them, whatever. And that's basically the shared random value that everybody produces. Okay, so this is very, very simple. The problem is that the last party to reveal ends up being in sort of a privileged position. So in a privileged position.
In an asynchronous mode.
Yeah, right. Well, so if it's totally synchronous, and
if you have to send before you receive the other one.
Well, that's, yeah, sure. If you have to send before you receive, that's hard though. I mean, that requires, that's very hard to enforce. Yeah. Okay, so, so why do I say Carol's in a privileged position here? So at the time when Alice and Bob have revealed their values, Carol is able to compute what the final result will be. Right, because Carol knows her value, which she hasn't published. Alice and Bob can't compute the final value because they don't know what Carol's contribution is. So, Carol has 2 advantages here. She knows what the output's going to be first.
What are the
reveal happens after all the commitments are there.
Exactly. So, but at this moment in time, Carol has not revealed, so nobody can compute the result except Carol, right?
I thought that the time of RANA reveal is after all the commit are there.
Okay, so Carol is committed. Yeah, she.
You're synchronous in
Yeah, so I should be clear. These are not like this is not one synchronous time step and another. This is just a weak synchrony here. So you're saying like Carol has already committed to her value, right? Yeah. Okay, so. The 2 problems, right? Would you agree that Carol will learn the result first if she's the last to reveal?
Yes, she knows the result.
Right.
But all she can do is hold back and not
And not publish.
And not publish. Yes, she can do that.
Sure, but what do you do in the case that Carol doesn't publish? If that forces the protocol to be rerun, then Carol has gained, right, a 1-bit choice on accept this value. And say this value, say they're just picking a winner of the 3 of them. If this value says Alice is the winner, Carol cannot publish. And then if you restart, she again has a fresh 1/3 chance to win. Right? So being able to abort actually gives you the ability to control the final result or to influence the final result.
So there are 10 Carols, right? And she has 2 to the 10 possibilities to...
Yeah. So it's true that... Exactly. Okay. So you can sort of fix this if you have a penalty, which is what people have tried to do in the blockchain space. This is one of the early papers about Bitcoin, which was really, I guess, Stefan's not here today, but it was his work with some colleagues. They showed how to actually do penalties for the first time in Bitcoin. So really neat. There's been a lot of other follow-up work on this showing that you can kind of fix this, but it requires having a penalty. Okay, so if you have a penalty if Carol doesn't reveal, I mean, you need a penalty for everybody, then this might be made to work.
What NA, NB?
Oh, this is just like her random value, and this is the, the opening to her commitment.
It seems to me that if you've got a large group here, then you could say in the next round, Carol didn't reveal, so she's not going to play the card in the next round.
That's still might be okay, right? I mean, it still might be worthwhile for her. But yeah, I mean, if the punishment is worse than the loss of losing the lottery, then people will reveal. That's the assumption, but that requires having some ability to punish people, right?
And also punish them more than they could gain by
yeah. But you need some way to punish. Okay. Another way you can do this, this is a little bit more complicated cryptographically, but basically a similar protocol. Everybody commits to a random value, and then you also encrypt. Might be missing something here. Okay, yeah, this either the slide got cut off or something's missing. But the key idea here. You commit to your value. You also, so Alice will encrypt to Bob's public key and to Carol's public key, 2 different secret shares. And then you also need an encryption of what your committed value is. So there's kind of one thing, I apologize, missing from the slide. And then you have a proof that everything's actually consistent. So you have to prove that you actually encrypted secret shares and that when combined, those secret shares will open your commitment, which, again, there needs to be like an encryption of this RA here for this to work. Okay, but basically, same idea. Everybody commits to a value, but now you publish all this extra data. And the reason that's useful is that if we get to the same situation, if Carol tries to abort and not open her commitment, there's enough information here, so Alice and Bob sort of publish their secret shares, and then Alice and Bob are able to actually recover Carol's committed value if Carol didn't publish it.
You remove the problem from 1 person to 2. I mean, if two of them gang on the third.
Yeah, so this is important. So now you're sort of assuming an honest majority, which is, it's a different trust assumption than before. But you're able to recover and you don't need an explicit penalty. So this thing, if there's an honest majority, this protocol should always finish, which is kind of the, generally I think there's an impossibility result that for MPC generally, you need an honest majority to be sure that the thing's going to finish and that nobody will learn the result if other people don't learn it.
Stronger. If you don't have an honest majority, you cannot do fair coin flipping at all.
Yeah. So there's some kind of somewhat related ideas. So I think they're all forms of MPC, but for the Dfinity blockchain, they do threshold signatures to generate randomness as a group. And it has the same property that if a subset, if a minority goes offline or doesn't participate, the majority can still produce the same result. Okay, and then the other paradigm, which I guess I'll talk about more. How long am I supposed to go for, by the way?
You're the last speaker.
3:50 is what we have on the schedule.
Okay.
It's very interesting.
Okay. Well, I have to at least show this. So this is the really slick kind of modern way to do it that dates to. Oh, I don't have the citation on this slide. It dates to, I believe, 2016, a paper by Lenstra and Wesolowski. So this protocol is really, really simple. Everybody just publishes their random contribution directly, so there's no commitments, there's no crypto at all, you just publish some random value. And then you compute the beacon output as some combination of everybody's random input run through a delay function. And that's it, so that's the whole protocol. And this delay function needs to have this property that the minimum feasible time to compute it is longer than the window that participants have to publish their share. Okay, so this is a very important assumption that this delay has to actually be slow to compute. But once you make that assumption, this protocol just sort of works and can't be manipulated. Why? So if we if we go back to this point and freeze, you know, Carol might even see Alice and Bob's random contributions, and she can pick whatever she wants. But she can't actually compute what the impact of any value she picks is on the final result, because the time to actually compute this combination and delay is so long that if she tries to compute it, she'll miss the deadline. Okay, so this is kind of subtle, but it's like a very, very powerful idea that if you can make this thing slow to compute, you can put people into this kind of no-win situation where they're either publishing something and they have no idea what the impact will be, or by the time they figure out what the impact will be, it's too late.
It depends on the computing power of Carol.
Not the computing power, but the computing speed. But so we'll drill down on that. So this is a strong assumption that you have to have. You know, she can't be able to speed this computation up. But you know, we've been working a lot on this problem.
So there's a small nuance difference here. Before you didn't have a deadline, right? You could wait for commitments, you know, however long it took. And now there's something different in the protocols that needs to be.
Yeah. So you basically need, you know, you need some like partial synchrony bound, and you need your VDF to be much bigger than that. But you need some ability to say like this thing was, you know, published on time or it wasn't published on time.
Way to abort, right? Which is not to manipulate the result, but right, Carol can not participate in the round suddenly.
Sure, but I guess at that point that's just denial of service, right? She can't abort in an intelligent way that will have any bearing on the outcome. But that's definitely true that, you know, that this deadline is functionally a little bit different here. In the blockchain setting, this is fairly natural. You just sort of say like it has to be published by this block, you know, yes or no. In some other settings, it might not be quite as obvious how to enforce this deadline.
Something similar from 2000, when Bonneau had.
Oh, yeah, timed commitments, yeah. So I had a slide for this actually, but I thought it was like too deep in the weeds. But I'm glad you brought it up. So there's a old idea of how you could do this protocol too, where you it's still a one-shot sort of, well. That's actually not a one-shot protocol, though. It's still two, because you still normally commit and reveal, right? You only, right?
But then it has the advantage that if everybody does participate honestly, there's no waiting. You open it up right away.
Right. Yeah. Well, it's 2 rounds, but yeah, then you don't have to actually compute the thing. Yeah. Yeah. So it's a really interesting protocol. I mean, it uses a different like delay primitive. Slightly.
You still need the deadline, right?
Yeah, you still need a deadline.
Everyone works fast. You don't have to wait till the deadline passes. You don't have to do this computation.
Yeah, so it's definitely like a downside to this approach is that, you know, even though it's communication efficient, kind of maximally, because everybody only has to publish one thing, you have to wait. Somebody has to actually compute this thing. Yeah.
I got the impression that you were an advantage of this over the Definity style thing, that there wasn't a threshold. Is that part of it? I didn't quite catch it.
There's no threshold here. Like, so actually, let me show you my next slide if it helps. So, I mean, the main advantage with commit and reveal, or with this delay protocol, or Lenstra and Wesolowski called it unicorn. The trust model is that you only need one party to be honest here, right? Whereas the MPC-based approach is you need an honest majority. But, you know, the assumptions are much stronger. Either you need some way to punish people who abort, or in the delay case, the VDF case, you need to make some stronger assumptions about limits on hardware and how fast you can compute something. Does that answer your question about why it's sort of better?
Denial of service. It just seems like, for example, I think Ethereum is using this. I wonder, for Ethereum or for another system, is there some sort of threshold that you're using on the number of people that you're going to use, or is there? I just wonder if there's some mechanisms that.
Well, the idea of how to actually instantiate this in the blockchain space is basically that you apply it to the entire block. And that way, like, anybody who wants to participate just has to get any transaction in the block, and then they've sort of influenced the result. Does that make sense? So, so it's kind of a little bit less explicit than this. There aren't named parties. The parties are anybody who is publishing any data in a block.
Got it.
Yeah, and these things are really every transaction in the block. So you just have to get a transaction in, and then you've participated.
Okay, thank you.
Yeah.
This is also robust, right? So if the bound in time is set properly, then even if the third guy doesn't speak, you can just ignore him and extract randomness from the two, right?
Oh yeah. Which is exactly. Which is why I was saying, like, you don't actually need to know the set of participants. You just go with whoever publishes a transaction in the block, and as long as somebody does, then you're kind of okay. Okay, so that's kind of why this is maybe an appealing protocol. Let me. Well, let's see. So I should be getting to the end actually, but I could talk for a lot longer about this. Let me skip talking about the blockchain stuff. I'd be happy to present it later if people are interested. Let me just talk about the crypto primitive, the new crypto primitive, and tell you sort of where that's at. Okay, so kind of a new crypto primitive that's evolved in the last 2 years. Basically, 3 different groups were working on it. Ironically, I was working on it with a group at Stanford. We had sort of the least good construction, but we published our paper first, so the definitions and name have sort of taken mostly from our paper. As I'll show you, the constructions that are actually the most promising came from the 2 other folks working on it. So VDF is a verifiable delay function. It's a crypto primitive. Basically, there's a function that you can evaluate on any input x. It gives you an output and a proof of correctness. And then, obviously, given this proof, the input and the output, you should be able to check that they're valid. And it should be very efficient to verify. Okay, so verifiable means more efficient to verify than just redoing the thing yourself. And this evaluation should be sequential. It should take t steps. And t is a parameter that you can specify. So if you want the function to take at least 2 million sequential steps, you can just specify that, and then you can pick that number based on what the real-world delay that you want is. Just a security parameter, standard crypto parameter. Okay. So the sort of historical note is that before, I guess, 2018, people had thought about doing every combination of 2 of the 3 of VD and F, but not all 3 at the same time. In particular, if you just want a delay function, you just have to iterate a hash function. That's pretty easy. If you just want something that's hard but not sequentially hard, lots and lots of examples, but computing a discrete log is one. And then a little more obscure, if you want something that is efficient to verify and provides a sequential delay, not a unique function, there were these constructions called proofs of sequential work that I believe were first published in 2010. Haven't really been used for much and sort of use a different technique, but it's a pretty cool construction. The idea is you build a hash chain, but you actually add a bunch of edges. So each node here is the hash of all of its predecessors. This thing's a depth-robust graph. And that way, and then you randomly open, you get to this point, you sort of do a Fiat-Shamir thing, you hash this, and then randomly reveal a bunch of these edges to check. And the depth-robust graph gives you the property that unless you cheat in lots and lots of these, there's still a very long path in the graph, which means it's sequential. So kind of the key part of it is the depth-robust graph, which also makes them kind of unwieldy, but it's a cool construction.
Much more recent one.
That's better, yeah. Yeah.
Very simple one.
Yeah. So it's been improved since the original construction. It's still kind of, I think, worse than the modern VDF stuff in practice. Okay, so how do you build a VDF that has all three properties at once? The sort of obvious solution is you just take you take something that's a delay function and you use any sort of generic verifiable computation to get a succinct proof. This works. It's not very efficient. If you do this kind of naively, if you tried to do a proof using libsnark of like 2 million hash functions in a row, the proving time would probably be quite long. So by itself, this proves that this is possible, but doesn't give you a very practical system. Let me just show you the one that actually turns out to work. It's very, very simple, actually. You just take your input, you raise it to the power 2 to the t, so it's just t squarings of that input in a row. And then you have to have some way of verifying this. I think I'll skip showing this whole proof. Let me give you the high-level intuition, well, kind of the amazing thing. Until 2018, we didn't know how to do this proof, in a more specific way than generic techniques. And then within 2 weeks, in June 2018, there were 2 separate papers published that had 2 totally different ways to do this proof by two separate people. And since then, a lot more people have looked at it. We haven't found really anything else besides kind of rehashings of these 2 general ideas. So kind of neat that out of nowhere we sort of came up with, well, I shouldn't say we as to take any credit. I'm not either of those people. No. They have like very different structures, the 2 proofs, which is why it was really, really interesting. And like I said, we've looked since, and we haven't found anything else. So it almost seems like there's 2 different ways to do it. But I'll skip the algebra in the interest of time. But basically, this is the Peterzak proof, and this one is sort of iterative. So you split the chain in half. It starts with just a way to check that this is the same exponent chain as this. So you kind of split it in half. But the really cool observation is that you can actually repeat that, and you can do a kind of binary search, and in a logarithmic number of steps, you can prove that the whole chain was computed correctly. So very, very neat. It's if you're interested, you should definitely read Ben Wesolowski's paper too, because it's a totally different proof structure that's very, very elegant and cool. So we know how to do it on paper now. VDFs are still not a thing in practice yet, so I'll just sort of highlight the challenges that we're sort of debating. One of them is which group you want to do this in. I presented it mod n. That's the most natural one, to do it in an RSA group. You can do it in any group where nobody knows the order. The classic way to do that is to have a trusted setup, which chooses 2 large prime numbers and multiplies them. Abi, who had to leave today, but he and others have been working on doing this using MPC, trying to scale up MPC to have like 1,000 parties as their goal, compute an RSA number, which is pretty cool. It's beyond the bounds of what has been done before. So if that comes together, then we can use RSA groups, which are really well known, to do this. This UFOs idea, I don't think anyone's seriously pursuing, but it's interesting. The other way to do it is to use class groups, which are a different group structure. Hasn't been, as far as I know, used in practice for anything yet, but it was published, with regards to crypto a while ago now. But this is a way to get a group of unknown order without a trusted setup. So all you have to do is choose a prime number, public setup. There's no trusted setup, and then you have a new class group to use. I should say that the really interesting challenge here is to use a VDF, you have to reason very carefully about how quickly an attacker can build hardware to compute this function. So we have more confidence that we can reason about how much you can speed up squaring mod n. That's a relatively simple function that's been looked at a lot, and people have built hardware before for it. The class group arithmetic, we don't know as much. There's a startup called Chia that's actually doing a contest to see how fast people can do this in software. And the goal is to move to hardware and hopefully, I guess, and have a future contest. There's sort of some economic questions, like who should compute the VDF. The Ethereum Foundation sort of views it as a public good. So they're planning to spend on the order of a few $1 million building hardware and maintaining that hardware and running it to actually, to build a beacon using a VDF for Ethereum 2.0, for both for consensus and for smart contracts to be able to use. But it's kind of interesting because, like, on paper it's scalable. Only one party has to compute the VDF. But in practice, you still have to spend millions of dollars to build hardware. And it's not that useful if you haven't built hardware. And that's like a big one-off upfront cost that somebody has to pay. So it's nice that the Ethereum Foundation and a couple of other cryptocurrency foundations have pledged to donate money. But it's not clear for other applications, how you would solve this problem. And the last thing I'll leave you with, kind of an interesting challenge. People in crypto have worried a lot about scaling, doing a lot of brute force. They haven't reasoned too much before about how much you can accelerate a single computation, which are very, very different problems. If you want to build one piece of hardware that solves one problem really, really quickly, you can start thinking about sort of very exotic, exotic semiconductors, lots of different things that really the crypto community hasn't had to deal with before. Hopefully we're gaining some new expertise on that and not making huge miscalculations in how fast stuff can be computed. But it's interesting that we're at this point now. Okay, why don't I take questions?